All right, welcome back. We're going to go ahead and get started with APC. These are some PowerPoint slides. Again, I haven't opened up the Unit 8 tab for APC yet. Eventually I will. We're supposed to be reviewing technically for our test tomorrow, but I guess we're going to go ahead and move forward with Unit 8 and keep on going. Alright, sorry. Okay. Well, I mean, knowledge is free, so feel free to learn. Dude, imagine us returning to our leader. Sorry. Okay. Alright, anyway. So yeah, I guess no test tomorrow. AP1, I hope you finished your binder check. Just have it ready. Eventually I'll collect it Q4. And, yeah, alright. So APC, we're just going to move on with Unit 8, which is Magnetism and Electromagnetic Induction. Okay. Now, you do have to start with your chapter summaries. Yes, chapter summaries, and that's chapter 29 and 30. Okay. Let me swap. There we go. Let's go and rename this. Unit 8 3 dash. What is today? The 16th? Oh, yeah. Magnetism. All right. So APC. Do chapter 29 and 30. Summaries. Should we take a quick... How do we do poll? Is there a way to do polls here? Poll as in turn it in on Canvas this week, or wait until we get back to school to hand them in by hand? Strawpoll.me. Yeah. Oh, yeah. I don't know, but democracy doesn't always work, especially in school, so the Stalinesque Iron Fist rule says do them by hand, and then scan them in so you can take a picture of it, or if you have an old technology called a scanner, you can scan them in and then turn them into Canvas. So yeah, do by hand and turn into Canvas. So let's see, when should we do it? By Saturday. So that's the 21st. First thing you get is homework. Alright, well, we still gotta get through APC, E&M, and get all those fives, and get you going to becoming electrical engineers and stuff. Alright, so do your chapter summaries. We'll start there. And the official phone? What? Venmo. You can't 3D print, obviously. I don't know what you're talking about. Alright, moving on. Let's go to PowerPoint. Boom. Magnetism. How do they work? Go and title your notes. Are all other schools closed? I think pretty much, like San Diego, Anaheim, LA. Yeah, we're pretty much. And the CDC is actually reducing the gathering number to 50 instead of 250. So, yeah, just stay by yourself, stay home, make sure hopefully you have enough food. Yeah, let's not talk about that one. 8 weeks. Oh, God. All right. Anyway, first slide. Boom. Magnets. How do they work? It's pretty much magic. Uh, Now you want to differentiate magnetism from the electrostatic force. Now they're similar, but one begets the other. You can create one or have one from the other, etc. You can use electricity and create a magnetic field, and then you can use a changing magnetic field um, to push around the electrons and create your current. So you can get one from the other. People who are tuning in the stream, make sure. I'm hoping that you'll rewatch the actual video, so you're paying attention. But remember, if you just pay attention now, you don't have to do it twice, so it saves you time. Anyway, they are similar yet different. Instead of having positive and negative charges, we have south and north poles. Okay, again, this is written by convention. We just needed two things that are different. We just like if you tuned into the AP1, I talked about how you could have had blue charges and red charges if you wanted, but we used plus and minus. Are north and south actually plus and minus? No, they are different from plus and minus. But magnets use magnetic fields, whereas your electrostatics is in the electrostatics field. So if you recall that space is like an onion and has many layers. Can you add royalty-free music over this? It would make it sound. Yeah, I know, right? But I don't want to. I don't know how to get that. But I don't want the audio to get like blurred out or whatever they do, muted. So I'm kind of scared. Oh. 1 second, nice. I'm doing it at 5,000 Mbp or kbps or 5 megabits per second, so you can get high quality 1080p. All right. Anyway, let's go back. So we have this onion. We have many layers. We talked about a few layers, and we had the electric field layer. But now we have a different layer, which has to do with magnetism, and this is the B field or magnetic field. Oops. Well, as you know, we have many layers, and all the layers kind of superimpose on each other, creating the universe that we know. What we see is all the fields all at once. The electromagnetic field, as you may have learned in chemistry class or something, again, is two different fields altogether. In reality, these two fields are actually 90 degrees to each other. So if you can imagine the electric field in one orientation, the other one is 90 degrees to it. Like so. Oh, I couldn't draw that. Let me try that again. All right. So the electric field is 90 degrees to your magnetic field. So here's our field that is planar here, and then we have a vertical one. Essentially, when something that oscillates both fields, right, oscillates both the electric and the magnetic field at once, so you might get a vibration that happens vertically in one field. So let's use orange for this one. So imagine a vibration going this way. There's also a vibration in the other field 90 degrees to that. So this wave is oscillating, horizontally, sideways like this, and vertically at the same time. It's kind of hard to draw. I have no idea what I'm drawing right now. So if you can imagine this magenta colored one being 90 degrees, 90 degrees to the orange one. Okay, so essentially, light, like photons of various frequencies, oscillate both the electric and the magnetic field at the same time. Um, it is not longer a field sandwich. There is a toothpick. What? Okay, we're getting lots of trolls. Anyway, we are vibrating both the electric and magnetic field at the same time. So when a photon, recall that the photon is gamma, when a photon is moving through, it actually, let's use a different color, it actually vibrates or oscillates in both fields at once. And so it's a wave, the electric and magnetic wave, that is oscillating. Okay. Okay. You should know a few of the EM wave spectrum, starting with I'm sure the Science Bowl people can help us out. Is anyone else's stream lagging or is my internet trash? So here's the thing. I am not a partner yet, therefore I can't actually do the variable bitrate stream where you can actually choose to watch it in 1080p or 720p or 480 based on the type of connection you have, or you can do it on auto, and then it'll auto select for you whichever connection is best based on your bandwidth. But until then, the live stream is at the highest, it's at 5,000 megabits per second at 1080p. But once I upload it to YouTube, you can choose variable bit rates, variable resolutions, and then you can watch it at a different rate. So unfortunately, until I get partnered, I can't actually do the variable bit rate on live. I have to do it through recordings. All right. Anyway, you should know the electromagnetic field. Let's start with radio waves. Where are my Science Bowl people? Go ahead and go from high lambda to low lambda. We'll go ahead and subdivide this into 7 sections. Guama, is at the end, gamma rays, with a very low wave or very short wavelength. Said that in the group chat, and it went from 9 people to 17 people. And it's high frequency. Okay. There we go. Sword Hero saves the day. Radio, micro, IR, visible, UV, X-rays, and gamma. Good. So radio waves, they're your all the what is it, 710? Oh man. Today was the first day I didn't listen to 710 on a Monday. Usually I listen to that when I'm driving to school. And of course, lambda and F are inversely related. Radio, and then we have our microwaves. Radio waves are huge. They're anywhere from yay meters, something like 1 or 2 meters long, to hundreds of meters. It could be the size of mountains. And then micro is typically the size of a microwave, or like a skateboard or something. And then from micro, we have our infrared, which is IR. And then followed by this small sliver we call visible light. And this is visible light because it's the light that our eyes can accept. Okay, so remember, what we see is just photons crashing into our eyes, into our rods and cones and all these cells, and then those cells get excited, send an electron down through their neuron pathway. It's basically a circuit through the wires that are in there, and then eventually it goes into your visual cortex, which is the backside of your head, and so when you get hit in the back, your eyes go black. But anyway, once those electrons arrive there, your brain creates a virtual image inside, and then you get a virtual image of what is in front of you based on the type of photons that you got. Now, if we can control the photons that you receive, we can essentially control what you see. Ooh. Hey, can you explain how antennas can capture radio waves while being shorter then the waves themselves, the electrons. That's a science bowl question. Basically, antennas work through resonance, and we're basically shaking the electrons back and forth at the same frequency as the wave itself. Anyway, go buy those almanacs, Jacob, and just start reading those almanacs so you can beat NoHo. I'm out of science bowl. Oh, too bad. So sad. Anyway, we have our visible light, and so visible light, and again, based on the size of the spectrum, visible light is a very small sliver of it. And then after that, we have ultraviolet, and then we have our X-rays. Okay, so radio all the way down to gamma. Of course, the higher the frequency, I should say proportional. Higher the frequency, the higher the energy. How do we find the energy of light? Wait, this is something that you should have remembered from the quantum electrodynamics. There you go, HF. Energy is equal to Planck's constant times the frequency of light. Good. So obviously gamma rays are super high energy, X-rays are less. There are no real hard boundaries between these 7 sections that we have: radio, micro, infrared, visible, UV, X-ray, gamma. It's just, a very high frequency X-ray is kind of on the verge of being a very low frequency gamma ray. What's Mr. I think it's just my name. But if you go to zphysics.net and then go scroll down, and it's the same one as our music video that we have. All right, what's your question? Hurry up. I wish you guys used your name so I can, or at least something similar, or at least used your Pokemon Go name. Oh no, don't post. Oh, okay. Thank goodness. Please be careful. Don't start posting links, because obviously I don't want to get banned before I set up like moderators and stuff. So anyway, I'm Justin. If you haven't. Oh, okay. Cool. Kawaii kimchi, great. All right, so we have our 7 sections again, and there are no hard boundaries between them. It's just it's all gray area. They kind of mishmash. But visible is kind of a hard boundary. It's based on how much we see. Again, actually, I shouldn't say hard boundary, because some people might see a few, hertz higher or something, a redder red or a purpler purple, if you will. So ultraviolet is basically a violet, a purple color that is just beyond the purple that we cannot see. Therefore, essentially, as you increase the frequency, the purple eventually disappears and we can't see it anymore. Infrared is a redder red, meaning if you stretch out the wavelength of red, it essentially goes invisible to us. So here's red, and then as you stretch it out to a higher wavelength, lower frequency, it eventually disappears and you cannot see it anymore. Remote controls, yes, use infrared light to send the signal, of course. Now, you might, if you actually stared into it, you might see a red light coming out of your remote. Now, that red light is not the infrared, obviously, because you couldn't see it. That red light is there to indicate that it is sending out the infrared, because you can see it. So that way you know that your remote is working or not, right? Night vision goggles, those are sensing infrared light. Infrared is basically from your heat, so it accepts the energy of that photon, and based on the energy of the photon, you color it in different shades, typically from blues and greens to oranges and reds. And we actually have an infrared camera. Unfortunately, it's at school. Oh no. But anyway, color coded based on the energy that you get, And so you essentially can see, even though there's no visible light, you sense the infrared light. Do the sensors resonate with IR? Yeah, the sense. So imagine solar panels. Remember the solar panel thing I showed you? Imagine solar panels accepting infrared photons instead of visible light photons. So similar thing, but except you call it a photoresistor, and the resistor accepts those types of photons. Who's RGX? Is that Nishank? Oh, Andrew. Andrew Vu, why are you always in our class? Are gamma rays dangerous because they have high frequency, so they excite cells to the point of death? Ah, I see. No, you turn into the Incredible Hulk. Typically, high frequency energy kind of phase through, but if you so if you accept that energy, especially during your cell replication, that replication process can go haywire, and then your polymerase might malfunction and doesn't know when to stop or something, and you just have uncontrolled cell growth, and that you keep on going, and that's basically what cancer is. But the other thing that could happen is that during the replication process, you put in different nucleotide. Nucleotide, because you just messed up a little blip, and now you have a different codon, which if you recall from biology class, that codon corresponds to some sort of amino acid, and now you have a different chain of amino acid. Your protein that is supposed to be made doesn't function properly. Your cell is now and so on and so on. It just gets worse and worse. It's all downhill from there. All right. There are bugs and slugs and other things that can accept different kinds of light, beyond the visible spectrum that we can see, and they can basically see colors that we cannot, so like UV colors and stuff. Anyway, that's just basic middle school things. You don't need to know everything. It's just a really good way to keep everything into perspective, so we know what we can reference when we're doing all of this stuff. The actual electromagnetic wave part, which is chapter 31, is not in APC. Remember, we're doing only 29 and 30. All right, so magnets. Based on this just one field, the B field, finally, back to magnets, we have a North Pole and a South Pole. Oops. And from our PowerPoint, you can see how the two norths repel each other, the two souths repel each other. And if you have opposites, of course you have attractive. Similar to electrostatics in that plus and minus attract. Plus plus repel, minus minus repel. Okay. Now inside the magnet, we can let's see. Oops, I'm clicking on the wrong screen. I have 3 screens going. Yeah, Andrew, keep it clean, please. We are technically in class. Here we go. Second slide. If you break a magnet in half, so I'm sure you've done it. If you drop, most magnets are made of ceramics. Even your neodymium plated magnets are ceramics on the top, and they actually shatter. I know from personal experience, of course. So as soon as you drop it, it shatters, and when you break magnets into smaller and smaller pieces, you can't actually separate the south from the North Pole. Okay. At the break, you create 2 new north and south poles. Okay? And as you break more and more, okay, you keep creating miniature-sized magnets. So what's happening? Let me show you what's happening on the inside. Okay. So typically magnets, are in the olden days, they were called lodestones. They were magical rocks and stuff you were digging up, like iron and stuff, and they had magical, mystical properties. Of course, magic is just called physics now. Yeah, this is big, and you got to learn it on your own. 20 sections. Slight work. Uh, let's keep it consistent. I think, what was it? North was on the right side, so we'll do north here, south here. Here's it's called a bar magnet. Nope, shape of a bar. Okay, so we have a north pole and south pole. What's happening is that every region inside the magnet. So if you subdivide these regions, okay, you can imagine them being like districts inside a state, right? This is how you can manipulate votes and stuff. The reality is that in each region, the electrons are, I guess, spinning in a certain direction. It's the spin state of the electron that gives you the magnetism in the first place. So if you imagine minus sign, for AP Gov students, that's called gerrymandering. Anyway, if you have electrons, we want to use the left-hand rule, LH, left-hand rule, LHR. Okay. All right. So imagine the electrons are spinning, and use your left hand, kind of like the torque thing we did. Okay, you want to curl your fingers in the direction of the spin, not just torque, but like angular momentum, if you will. The way you're spinning is the curl of your fingers, and your thumb gives you the direction of the spin, right? So when electrons are spinning, let's say they are spinning this way. Okay, I should use a different color. Okay, is it spin up or spin down? Audience. Use your left hand. Imagine the electron spinning. Okay. If you take a helicopter point of view, right, look at the electron spinning around from a helicopter, assuming you have a miniature helicopter, magic school bus, you can see how it is spinning clockwise. And of course, battery's running low. Where's my plug? Oops. Excuse me. All right. Okay, we are good to go. All right. Helicopter point of view, you can see how the electron is spinning clockwise. Now recall, the right-hand rule has positive things moving, not negative things. So that's why we're using the left hand instead. Counterclockwise was up for positives, but for negatives, clockwise is up. So using your left hand, this is spin up. And so if you reverse the direction, of course, you get spin down. Positive charges, you would do right-hand rule. So if I had in a different part of the galaxy, we have our positron. And so if this positron was spinning in this direction, then you can see using the right-hand rule, oops, let me use the same color. Right-hand rule. You can see how it is spin down. Oh no, what happened? Oh, there we go. It is spin down. So all right, yes, negative RHR, which is left-hand rule. Okay. So the magnetic moment, similar to electric field lines, Okay, electric field lines. Remember, electric field lines are radiating outwards out of the plus into the minus. Similarly, we have magnetic field lines that come out of the north and go into the south. So you can associate north poles kind of like the positive charges in electrostatics. Typically, in ordinary things, they both come in pairs. Poles come in pairs. So you get a north and a south. When you break it, you can't really separate it. Now, is there a magnetic monopole? Apparently, theoretically, it is possible. If you can trap it inside some weird stuff, I have no idea. This is beyond my level. This is beyond APZ. Some sort of time crystal or something. I don't know. But in any case, for everyday things, we get them in pairs. And so the field comes out of the north and then goes around and goes into the south. Okay, on the top side, oops, it would go out and then into the south. I should move it. Oops. Okay, so out of the north, into the south, out of the north, into the south. And so the further out you are, of course, it's weaker, just like any other field theory. So it doesn't go through. Yes. Hang on tight. You are one step ahead of us. And so the ones that are closer will have to go further out. Whoa. And then eventually come back. Ooh. Okay, and just like our field theory, of course, the one that goes straight will go around the entire universe and then come back down. Pew! Yay! All right. So, and just like field theories, of course, the further out you are, the weaker the magnetism is. And now for the inside, in the inside, and this is what's going on. This is why we broke it up in the first place. These regions, these are called domains. So imagine being like a district inside a state. Okay. Oh, Stephen Gong has joined us, and he got it. Domains. Good job, Stephen Gong. We'll give you a wireless high five. Wireless high five. So these are our domains. And on the inside, the direction is actually reversed in that the field lines are not actually field lines. They are field loops. They are closed loops. So this loop that came out of the north is actually closed off in that in the inside, it goes from south to north. Direction of B inside the magnet south to north pole. Okay, whereas on the outside, direction of B outside the magnet is north to south. Nani? So what's going on is that on the inside you have your domain, which is basically a region where everyone kind of thinks the same, essentially. All these charges have a similar direction of spin state, or the magnetic moment that you're creating. Now, they don't all have to be in the exact same direction, meaning you can have a region. Let's have this first region, this black one, being a vector. This is the summation, the net or the resultant vector of all the little tiny vectors from each little tiny charge that is spinning around, creating the magnetic moment in the first place. And so each domain has a general direction they point. Okay. Now, even within it, you might have little tiny zones. Theoretically, it's possible, based on the construction of the material, that are not exactly the same way. Uh-oh, I only have 10% of battery juice in my headphones. So here we go. It is theoretically possible, but in any case, when you have this vast majority that is all pointing together. Okay. What you do is you add all of the magnetic moment vectors together. Now, notice how each vector can be broken down into its components. So this magnetic moment vector representing this region of our magnet, it has an X component and a Y component. Okay, but somewhere else there may be a Y component that is opposite to our Y component in the first region. Essentially canceling out all the Y components, leaving just the single X component that moves to the right. And so in the inside, our field continue onwards. Remember, this field line is a loop. They are closed loops. There is no beginning. There is no end. During the creation of the magnet itself, or the poles itself, it was birthed in pairs. And so the vector sum gives you a complete direction to the right in this case. Okay. So domain, what is a domain? A region inside the magnet with similar spin states. Okay. Now, what we could do is use a stronger magnet, or something like an electromagnet, which we'll learn about later, to realign these domain arrows, these vectors. Okay. So by using a stronger magnet, we can force and tilt this arrow. Instead of going at some angle theta, we can reduce this angle downwards to make it more horizontal instead. This would mean that the X component is now greater and the Y component is less. So more of your vectors are pointing in the X direction, essentially increasing the strength of the overall magnetic field, or increasing the strength of the magnet itself. Okay? So when you remagnetize magnets, you're actually using a stronger magnet to realign the domains so they all point in the same direction, so that the summation of all the vectors inside give you the maximum possible resultant vector. Okay? How do you destroy a magnet? Well, similar to how you destroy electrostatic bonds, you can heat it up. By heating it up, you cause chaos within all of the charges that are inside, and now all the little charges are pointing in different directions, and the domain essentially has a zero net vector, and therefore you become demagnetized, or not magnetic. Okay? So there are certain materials like iron and stuff which you can freely magnetize, in that you can realign these domains to point in one way, and so you can make it a magnet. And this is a demonstration that I would have to show you if we were in school. Unfortunate. But and then if you heat up that iron, then you can kind of change the direction of the vectors and then cancel them out. Okay, yeah, it's kind of like polarization, but for magnetism. We are polarizing the spin states instead of polarizing the charges. We're not actually moving anything. We're just realigning the spin state. So if you imagine this electron that is spinning, remember it has angular momentum, assuming if it's, remember this is called a spin state. Whether or not the electron actually spins is unknown. The electron, for all we know, could exist as a wave. It's just a characteristic of the wave that we call spin. but it's easier to imagine it as if it's spinning. So this spin state has a direction, so we can realign this direction similar to how I moved around the spinning wheel. Okay, you can definitely feel something. They feel the torque or the along the vertical axis, perpendicular to the spinning plane itself. Okay. All right. So we can change the domains to point in the direction we want, and then we get a stronger magnet. Now, if you accidentally put the magnet in the wrong direction when you're remagnetizing, it is possible to turn the vectors all the way around to the opposite direction. And when more of your vectors turn to the opposite direction, then you can actually reverse the direction of your polarity, or change the North Pole and create a South Pole, change the South Pole and create a North Pole instead. Okay? When this change happens, it changes both things at the same time. So when the net resultant vector is pointing left, then instantly your South Pole becomes a North Pole, and the field lines also change their direction, essentially. Okay. So during the summer heat in the valley, some of my magnets that I store up, if I don't properly shield them apparently, have reversed the direction of the polarity. So even though it says north on one side, it's actually a South Pole. Okay, the way we map the magnetic field is very similar to how we got the electric field. All right, can anyone tell us how we map the direction of the electric field? What theoretical entity, substance, object did we use to map the electric field? No, not a multimeter. How did we Okay, that is your lab. That is true, and it turns out that the equal potential line is perpendicular to your electric field. But this is before. So think about AP1. What did you learn in AP1? AP1 student, you should know this. What did we use to figure out the direction of the electric field? Fed tutorial. No. It's something small. 10 seconds. 9, 8, 7, 6. Maybe we need some hints. Imagine having a positive charge. Boom. Okay, if I want to know what no, don't Google it. If I want to know what the electric field is here, which way does it point when we're to the right of a positive charge? Come on, AP1 student. What? Away from the Okay, so how do you know that the electric field should be towards the right, away from the positive? Why is it away and not towards? There you go. That's it. Mystery wizard. You got it. You got it. It is a small positive test charge. Ooh, a wireless high five for a mystery wizard. Okay. All right. So placing this small positive test charge, we map out the force vector. So what is the force on this positive test charge? Well, the force would be kqq over r squared, based on the separation distance from center to center. Okay, and we know that the force vector is to the right. And then what we do is we divide the force by the positive test charge, and we end up with the leftover, and the leftover is the electric field itself. So we're using a positive test charge to show us the direction of the electric field. So instead of using charges for magnets, notice how for the electric field, to mapping the electric field around a charge, we used a small or a smaller charge and found the force on it. So what do you think we're going to do for magnetism? To figure out what the magnetic field is, we want to map the magnetic force using a smaller magnet. Very good. That smaller magnet is basically a compass. All right, so using our compass, which is basically a tiny little magnet, typically they have a little needle that can point. Oh, what am I doing? Let me see if I can draw this. Of course, we have an axle, a swivel action, and then a needle, something like that. And this needle can turn sideways or whatever. Okay. Typically, if you have a magnetic field near the vicinity of water, you can actually put in a tiny little needle as long as it doesn't break the surface tension of the water. Uh, Chemistry students or AP Bio students, you should know. Surface tension is, remember how water bugs run across the top of a water? They don't break the surface tension of water. Basically, you can place a needle in the water, and the needle will reorient itself such that it points in the direction of the magnetic field. All right. Notice how we have the North Pole and the bar magnet on the right side. Okay. The field is coming out of the north. Okay. It's going left at this spot where I put my compass. Okay. So how will my compass orient itself? Remember, the magnetic field on the outside of any magnet, whether it's a big magnet or a small magnet, goes into the south side and comes out of the north side. So that means that this would point S and this would point N. So your compass is going to say that the north is that away. And when you're using a compass on Earth and your compass points north, okay, it is realigning itself with the magnetic field of the Earth itself. And this leads us to our next slide here, and that is the Earth is, where is it? Oh, there we go. Boom, this slide. The Earth is a magnet, right? Where does it come from? Consider being a geophysicist to learn more. Get a PhD in geophysics. But inside of our Earth, we have molten metals. Now, it's not just iron. There is actual other stuff like nickel and stuff, but they are molten. It is assumed that it's spinning around. Unfortunately, I can't. I can only do it based on things that I can test externally, obviously, and we have to infer everything else afterwards because we can't really dig a hole straight through. Which, if you recall, remember that problem where we dig a hole straight down and then we try to oscillate between due to the gravitational force? A classic physics problem. But anyway. It is assumed that we are spinning around, and that spinning molten metal and stuff is creating the magnetic field in the first place. Okay, and so Mars, which lost its magnetic field, means that it's kind of stable and not generating the proper magnetic field, or it could be that the domains are not aligned in any way in the inside of the planet to produce a strong enough magnetic field, whereas our domains are all lined up on the inside of the Earth, so that we have a nice protective shield. And when we learn about the magnetic force, we'll talk about why this magnetic field is very important, and it's the reason why we're alive in the first place. Or inside is solid? No, it is definitely hot. I mean, we know that based on just geothermal energies, right? When you dig a mine and you go down into a mine hole, you get more and more heat. It gets hotter and hotter. So we know that it is molten because of it's so hot. And even during the formation of the planet, you have to imagine it was super hot, of course. And when you cool something down, remember it cools down from the outside in. Kind of like when you heat up a burrito, The burrito on the inside is basically molten metal, and then on the outside, that tortilla might be nice and cool. So you might mislead yourself into thinking the burrito is ready to eat, and then you burn your tongue. All right. All right. So anyway, the Earth itself again is an upside down magnet. My hot pocket be heating from the outside. Very good, very good. Now, as you can see in this picture, the Earth is upside down. Not only that, it's actually tilted, which is also important, but not for us. We don't. We just need to know that it's slightly tilted. But it is an upside down magnet in that what we call the geographical North Pole, where the theoretical Santa Claus is. The geographical North Pole is actually the South Magnetic Pole. The South Magnetic Pole. And the South Pole is the North Magnetic Pole. Again, that's a simplified version because that would assume that the bar magnet that the Earth is actually straight, but it's not. And as you can see in this picture, it's actually slightly shifted, and it can actually turn. And over the course of thousands of years, the entire bar magnet can flip all the way 180 degrees around, and it does that. It's called, every hundreds of thousands of years. So sometime in the future, the South Pole will become the South Magnetic Pole again, and all of your compass or compi, plural for compasses, will point the other direction from what it is pointing now. All right. So as you can see, when you're on the surface of the Earth, your compass, your miniature compass, which is your small test compass, if you will, is pointing towards the South Pole, similar to how the North Pole of our compass is pointing towards the South Pole of our bar magnet. Okay, so the bar magnet of the Earth is on the inside of the planet. So this was the planet. Okay, when you're standing outside, so this is you standing on top of the planet, holding your compass, huge compass, huge. That compass is pointing towards the South Pole of the Earth. All right. All right. Back to the PowerPoint. Couple of other things that we should talk about before we end the stream. Compass is used to map the field. And then this is called a this is just showing you the inside magnetic fields, visualizing blah 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 blah. And finally, when you put two magnets close to each other, so the needle is a magnet, essentially, yes. Iron, which was the lodestone back in the day, iron kind of magnetizes itself. It realigns the domain inside the object, so that it aligns itself to the magnetic field that is present. So if there's no other magnetic field, then it will align itself to the magnetic field of the Earth. Okay, but if you put another magnet that is stronger than the Earth's magnetic field at that spot, you can kind of control the direction of the compass. So it will align itself to the strongest possible magnetic field at that spot. Again, if you have multiple magnets, the magnetic field lines, again, they're vectors, so they'll just add up with each other, and whatever the net resultant vector is, that's the direction that the compass will align itself with. Can you heat up a compass to mess it up? Yes. And then prank the magnet. Ban this fool. Go back to AP1. I need to figure out how to do it, but we also have to figure out who is trustworthy enough to be modded in the first place, right? I can't just mod random people. All right, so back to here. Here, what we're seeing is a uniform magnetic field. A uniform magnetic field. Similar to having a big giant charge. So if I had a big giant charge, we know that if I zoom in, and I am near the surface of this big giant charge, we would have a uniform electric field near the surface. So if I have a big giant magnet, we can say the same thing. One way we kind of overcame the necessity of finding a big giant charge, which is basically impossible, what we did was we lined up a bunch of. Oh no, no. I was supposed to be charging, but my charger, uh, my charger was not plugged in. Excellent. Oh my gosh. Can you still hear me? Uh, all right, we're still good. So we can still use our PowerPoint. Pays to have two screens instead of one. Uh, Remind me tomorrow. Actually, it's working. We're live. Yay. It didn't actually turn off. Okay. Anyway, so remember we lined up a bunch of charges together to create that uniform electric field so that when you have pluses, all the bent lines will go away, resulting in a net uniform electric field that point from the plus to the minus. Okay. Similarly, if you have a big enough magnet, so this is not just a magnetic monopole north. It's just showing you that it's a big giant magnet, so the other side must be south. And you have a second piece at its south end. Okay, your magnetic field lines, instead of going all the way around to the back side of your south end of the first magnet, it'll just find the easiest or the closest south pole, and the magnetic field lines will realign themselves so that they point from north to south like this. And of course on the inside it will go south to north, but we don't really care about that right now. We're just going to focus on the middle, or in the middle. And around the edges, of course, there are going to be some bendy ones. Ooh. Ooh. Like so. Okay. So even these ones are bent. Now if you zoom out all the way, this magnet is essentially a bar magnet where the middle doesn't matter. But on the left side we have a south pole, on the right side you have a north pole. And so if you zoom out, the magnetic field will look exactly like a normal bar magnet, in that the ones that are really far will be coming out of the north and then go back into the south end of the first one. Okay. On the inside here, between the two, we have a uniform magnetic field, B. Okay. How do we measure it? We measure it with the unit. Science Bowl, can you tell me the unit for magnetic field? It's a very popular name or word, of course named after a physicist. Yes, Tesla. Capital T, which is Tesla. All right. I think that's it for today. I am super tired. I'm kind of hungry. Time for lunch. So, oh my God. Anyway, ignore these trolls. No, not a wireless high five for that one. That was like worse than a dad joke. All right. Until next time, see ya. Do your chapter summaries. Bye.